This is how to solve problem 144 from chapter 13. As always, the full question is in the description, but for now, let's determine the rate of heat loss from an absorber plate by natural convection and radiation. So let's get the givens out of the way. And we have T1 is 80 degrees Celsius, T2 is 32 degrees Celsius. Emissivity 1 is 0.9, emissivity 2, 0.8, theta 20 degrees, length 0.03 meters, and sigma 5.67 times 10 to the negative 8. Alright. Now we gotta get, what are we finding? And as I said before, the heat loss from convection and from radiation. Alright, so first step is to find the average temperature. That is T1 plus T2 divided by 2. Real simple, 80 plus 32 divided by 2 is 56 degrees Celsius. Then using this, we get the properties. K equals 0.0277. And then we also get, ignore that dot on top, 1.857 times 10 to the negative 5. And we get the Prandtl number 0.7212. Now using this, we can get beta. Let's fix that. Okay, beta. And that's 1 over the average temperature in Kelvin. So we end up getting 0.003041 inverse Kelvin. Now that we have that, we can calculate the Raleigh's number. And T1 minus T2, the Prandtl number, and this is squared. Okay? So next, 9.81 for the gravity. Beta, we just calculated it. Next we have the temperature, so 80 minus 32, and the length, which was 0.03 cubed. Let's throw the Prandtl number in, which we got as 0.7212, and divide that by 1.857 times 10 to negative 5 squared. And plug that into the calculator, we get 80,857.878. Now we calculate the Nusselt number, and that's going to be equal to 1 plus 1.44 times 1 minus 1708 divided by the Rayleigh number cosine theta times 1 minus 1708 times sine 1.8 theta to the power of 1.6 divided by the Rayleigh number times cosine theta plus the Rayleigh number, cosine theta, and all this to the power of 1 over 3 divided by 18 minus 1. Now, we plug in the Rayleigh number with 80,857.878 and theta with 20 degrees, which we got from up here from the given, and plug it in. Yeah, I don't want to rewrite this whole thing out, so I'm gonna get 1 plus 1.44, and then this will end up equaling 0.9775. This will equal 0.9904, and this last term will be 1.353. We add those all up together and we get 3.747, and that's our Nusselt number. Now we move on and we calculate the surface area, which is just the height times the width, and that is just 1.5 times 3, and that's 4.5. Next we have to calculate the heat loss through convection. So we're almost done here. Convection, and that's K times the Nusselt number divided by L, surface area, T1 minus T2. This looks like 7s for a bit there. So plug it in, 0.02779 times 3.747 divided by 0.03 times 4.5. Oh, this is meters squared here. Times 80 minus 32. So now, for this we get 750. So that's the answer to the first part. So the second part, we have the heat loss to radiation, and that would be sigma T1 to the 4 minus T2 to the 4. And we'll see that this is 1 over the first emissivity plus 1 over the second emissivity minus 1. So now we plug in the values. So sigma was 5.67 times 10 to the minus 8. That was 4.5. And then we have, let's convert the temperatures to Kelvin. So that'll be 353 minus 305. And remember, this is to the 4th power. Then we divide by the inverses of the emissivities. Minus 1. And then plugging that all into the calculator, we get 1288.53. And that's how you do problem 144 in chapter 13.